Okay. Oh, what is this? Am I still in your seat?
Ah, no. Ah, no, I just put my smartphone here. So go ahead.
Like Sheldon, you have the preferred seat
Yes.
in the seminar room.
That's my spot.
By the way, how's the weather in Teruel? It's already cold.
Nice and warm. It's about 0 degrees, hence it's warm.
It's fine. You cannot complain, guys.
Alzamona.
Calimera Stadios.
Hi, Asterius.
We also need a book like Dark Energy Survey with Halalambre Variability Survey.
Okay, let's wait 1 more minute until okay, I think we can start. You are more or less.
No, io dicevo proprio il paper.
More or less full. So let me introduce you to Zahra Sharbaf. She's doing her PhD with Nacho here at the IAC, although she's not at the IAC at this time. And she did her degree and master in Tehran. And after that, she worked also with Nacho Trujillo and Mohammad. And today, she's going to talk us about the variance of galaxy spectra. So Zahra, whenever you want, you can share your screen.
Hello, everyone. Thank you very much, Juan, and thanks for giving me this opportunity. And I apologize you at the beginning because I have a bad cold, and I know that I am gonna cough a lot. So sorry about that. As Juan mentioned, I'm a second-year PhD student at IAC, and I am working on the multivariate analysis of galaxy spectra. Today, I want to present a study aimed at understanding the underlying physical phenomena of galaxy following a data-driven approach based on the galaxy spectra and variance of the galaxy spectra in a careful selected sample. As we know, galaxy spectra has a lot of information about the galaxy and almost records the formation history of the galaxy. And we can retrieve so many properties, physical properties of the galaxy by studying these SEDs. But I'm so sorry about the voice. But always retrieving the information from the galaxy spectra is with the problems, and it's difficult because of the large entanglement of the individual component of galaxy spectra, which also prevents us from the detailed study. And most of the time, by study the SEDs, we cannot go further than the average age and metallicity, the estimation of the average and metallicity. In general, there are three approaches to study the galaxy spectra. The first and standard approach is the model fitting. The building block of these models are SSP, simple stellar population, which are a group of stars that they are formed at the same age with same chemical composition and with a well-defined distribution of stellar mass or IMF. We can describe any formation history by superposition of the SSPs and combination of SSP. Comparison of SEDs with the population synthesis models can give us lots of information, and through the history we find so many fundamental constraints of galaxy spectra with this way, for example, like a correlation between the age, metallicity, and stellar mass, and other scaling relation of the galaxy spectra. However, still population synthesis model cannot be the comparison with the population synthesis model cannot be taken beyond the lowest order moments of the distribution in age and metallicity. And also we can use so many different codes for these spectral fittings, and we achieve the acceptable but different results. So there are other ways also to study the galaxy spectra. Machine learning is a method that people recently use it in the both unsupervised and supervised way to extract the information that we cannot achieve through the model fitting. Another way is multivariate analysis. By applying the multivariate analysis to the galaxy spectra, people try to reduce the problem to the blind source separation, and using the data-driven diagnostics such as covariance, clustering, or statistical independence, then in this way we try to overcome the entanglement. What I want to present today is belong to multivariate analysis. I want to use the covariance of the galaxy spectra as a main source of the information, and using the PCA, principal component analysis, as a method, try to understand what is the limitation of extracting the information from the galaxy spectra, how much information encoded there in terms of the statistic. This is what I want to answer. So before going and talk about the principal component analysis or PCA, I want to talk a little bit about latent space, which all of us are familiar with. And most of the time in physics, we try to reduce our problem to a latent space, unseen space, or unobserved space. This is the space that we don't directly observe it, but we can reduce our problem to it, and it's almost we believe that is the parameter or a space that control our sample, and it's the meaning of our sample, let's say. The best example maybe is the Hertzsprung-Russell diagram. We have the spectra of the stars, but then we, by the spectra of the star, we calculate the inferred parameters such as temperature and luminosity, and by having only these two parameters, we can talk about the life of a star. Also, a spectra of a star is a high-dimensional data, has so many entanglements and so many data points. So to create the latent space and understand the underlying physical phenomena of an object or a process, we need two-dimensionally reduction. What I mean by dimensional reduction, here you can see, for example, I have a scatter plot, a 2D plot that's plotted in the Cartesian space. This axis could be everything. And you can see another set of vector that it seems describe my data a bit better, and it's correlate along the variance that we can find in data. For dimensional reduction, what I can do is that I can perform a rotation in this axis and then try to align with the side that most of the variance of my data will get explained, as you can see in this video in the along the pink side. And what's happening is that I can project all the points that I have in these two-dimensional data along the sides that describe most of the variance in my data. And what I am going to lose is just only a scatter along the smaller axis. So I am not going to lose lots of information, and most of the variance in my data will get explained. This is dimensional reduction, and this is what PCA attempts to do. So we want to do the dimensional reduction by PCA. But of course, it makes more sense when we have the higher dimension data. For example, look at this donut. This donut is a higher dimension data, but we can see that we can almost describe all the points of this donut by a plane. So in principle, I can project everything to a plane and everything will get explained. About the galaxy spectra, imagine that we have a spectrum of a galaxy which has so many data points. By data point, I mean wavelength B. In a spectra, we have so many wavelength bin, and for each wavelength, we have the flux. Each of these wavelength bin consider as a dimension now for me when I want to do the dimensional reduction. We can define the covariance matrix, as you can see, between different galaxy spectra. And then that rotation that we apply in the previous slide to that Cartesian space, we can also apply a rotation in a higher dimension space and then find the vector or basis that carries the variance of the data. But how? By diagonalizing the covariance matrix. So what we do in PCA, we define the covariance matrix for the galaxy spectra, we diagonalize this covariance matrix, and then the diagonal matrix include the eigenvalue, and this U matrix include the eigenvector or information vector, or in another term also sometimes people call it principal components. That shows the variance of our data, and the size of this eigenvectors is equivalent to size of the data points that we have. For example, if we have 38,000 wavelengths bin, then we are going to have the same. But what we can do is that we can sort this eigenvector based on the amount of the information that's encoded, and it's on the eigenvalue. So we can do the dimensional reduction. And also I can project, this is this phi is a galaxy spectrum. I can project all the galaxy spectra to this eigenvector and then do the dimensional reduction for my data. So this is our methodology. But what about our sample? We have almost 78,000 galaxy spectra around the SDSS sample, but why only SDSS sample? As I explained, this method is based on the covariance and variance of the input data. So it's very, very important that we remove all the potential systematic from our sample. Because of this, we want to have the homogeneous sample. We just use only one survey, because if we use different survey, spectra from different survey, then we will add the systematic to our sample. And as PCA is very sensitive about the variance, that systematic is going to pick up as a original signal which can be run. Another thing is that I have so many restrictions that I apply to my sample that I explain here, is that first of all is velocity dispersion. We know that the stellar population, underlying stellar population of galaxy correlates strongly with the stellar mass or velocity dispersion. So we choose the small range of velocity dispersion to not be affected by this. And also a small range of the redshift to minimize the aperture effect, and also to not be affected by the noise. I choose the galaxy spectra with a high signal to noise ratio, also before this SDSS spectra assumed to have the high signal to noise, again, we apply this restriction. And one of the important points is that I remove the continuum. This is very important, and I have so many, maybe, I mean, it's interesting as well because continuum carry lots of information of a spectrum. And by removing the continuum, I almost remove 70% of the information that encodes in the spectra. I know that I am removing it at the cost of removing information, but continuum has a signature of dust reddening and also flux calibration. These two can be very important and strongly correlate with the variance, so it can affect our results. We just want to focus on the underlying stellar population of the galaxy, so we remove the continuum. Another thing that I do is that I don't want to be affected by the outlier galaxy. So when I am calculating the covariance, this is a covariance, and this term here is each element of the covariance matrix, which is the difference between flux of a galaxy in a given wavelength with the median flux of all the galaxies in that wavelength. When I calculate these terms of covariance matrix, I consider it to be bigger than 4 sigma, which sigma here is the standard deviation of the distribution of the fluxes in that wavelength. And this is applied to all the wavelengths. Of course, it affects our sample, and the size of the sample is going to reduce, but at least we are make sure that we aren't affected by any outlier inside our sample. Again, because we are very sensitive about the variance here. The last and maybe the most important restoration that I apply to my sample is that I separate the sample from the beginning based on the BPT classification or ratio of the line, intensity of the emission lines in the galaxies, to 3 subsamples of the AGN, quiescent, and star-forming galaxy. And the reason is that when we have only one sample, including all of this galaxy, PCA will pick up the signal that comes from the mixture of this stellar population, while we want to focus on the stellar population within each sample and then the comparison of this sample. And at the end, also, I show the result of if I use only one covariance matrix, what's happening. But so now consider that we have 3 different subsamples and 3 covariance matrices. In another term, I apply principal component analysis 3 times. Here, I show you 2 wavelengths interval because we are focused on the blue interval, as you can see, from 38 to 42,000 angstrom, and also red interval from 50 to 54,000 angstrom. The reason is that we want to focus on analysis in the wavelength bin or spectral interval that we know that most of the variance or difference from galaxy to galaxy is encoded in that region. Another thing that I do, I mentioned that I want to focus on the stellar population of the galaxies. I remove the continuum at the cost of removing the information. I also do not include the emission line in this analysis. The dashed region that you can see here are the region that I don't include them because they are emission lines. As you can see in the standard deviation of the spectrum of these groups, you can see that how the amount of variance here is huge. So if we consider them, then the principal component will be pick up those emission line or those signal as the most important one. While we want to focus on the stellar population, the pure stellar population, not be affected by the gaseous component of the galaxies, or another term, absorption line. Here in the plot below, you can see the first principal component of each subgroup in 2 different intervals. And as you can see, each of these principal components or eigenvector could pick up the most permanent absorption feature of these galaxies. So now that I have principal components, eigenvector, what I can do is that I can create the latent space by projecting the galaxy spectra to these eigenvectors. But before that, how many eigenvector I want to use? I wanted to reduce the dimensionality of the input spectra. Here you can see the scary plot that shows us the amount of variation in another term, eigenvalue that encoded in each of these principal component. And as you can see, the first principal component is the components that carry most of the variance in our input spectrum. And one interesting point here is that in two interval, we can see that the AGN galaxy, the first component of the AGN galaxy, which is the most important component, has the higher variance in comparison with star-forming and quiescent galaxy. And this could be because of the fact that we already know that the AGN galaxy are more variant population. We have different galaxy in the AGN sample, those ones that go through the quenching, or maybe those ones that go through the rejuvenation, and all of this. So we have more variant sample there. That's this maybe could be related to that. And also at the top of that, we can see that the quiescent galaxy has the less amount of information. That also could be because of the fact that quiescent are more homogeneous distribution. They are older star, they are that different, so they have the lowest amount of information there. Another thing that maybe comes as a surprise for you, if you are familiar with the PCA work, is that most of the time when we see this scary plot about the galaxy spectra, we can find that the first principal component has almost 70% or 80% of the information. But now you can see that the blue part that has more variance also, it's around 12%. And the reason is, again, the continuum, because there is no continuum, there is no emission line, and it's just only absorption line and the pure stellar population. So that's the reason that you can see that amount of information is not comparison maybe with the other works. So let's go and project the galaxy spectra to this component. Sorry, I forgot to mention that I limited our analysis to only 3 components. So we just only consider 3 components, and we project the galaxy spectra to them and create the latent space. Here, you can see for the blue part and red part of the spectrum, the latent space or the corner plot that we have. As you can see, the first principal component that carry most of the information in both wavelength spectrum, we can see that the galaxy puts the galaxy in the different place of the latent space. They are separated very well. And another thing that is interesting is that we can see there is a hypothesis of the transition between the galaxy biomodality. We can see that red cloud is red sequence is here. We have the blue cloud. Sorry, and we have the AGN galaxy in middle, which we know that AGN galaxy most of the time populates the green valley area. So we can see a sort of hypothesis of the biomodality here, even though the biomodality is the hypothesis of that people most of the time when they use emission line talk about it. But here we don't have any emission line, and still we can find that. Another thing that maybe people complain about it is that, okay, you had 3 different groups, and then you had 3 different covariance metrics, and then you create 3 latent space. They aren't the same. You just plot them in the same plot, but it's not true. This isn't a disjoint comparison, and the reason is that, sorry that I repeat myself a lot, but while we don't have the continuum and while we don't have the emission line, and the underlying phenomena that concern PCA is just only a stellar population, which we assume it should be the same among all the galaxy. So the main concern information is the same. And we also know that these components order based on the amount of variation that they encode. So if the first component is the components that carry most of the variance, I expect it should be the same among the quiescent, AGN, or a star-forming galaxy. And I'm sorry I forgot to mention, from now on, I consider that all the red color shows the quiescent galaxy, green is AGN galaxy, and blue is a star-forming galaxy. Another thing is that I wanted to, show in this movie was that maybe also you say that, okay, you plot them together, but what about the orientation? If we look on the latent space in another orientation, maybe we will find that there is no hypothesis of biomodality or they aren't like this. But in this video, you can see that it not matter in which orientation I look, the result will be the same. So now that I have the latent space, the next step is that to find out the physical meaning for this component. What are these components? Can I have any physical meaning for it and try to talk about the evolution of the galaxy? First of all, I try to find out the correlation of these components with the observable feature of the galaxy. Sorry. This plot, in the left panel, we have the general observable of the galaxy, and in the right panel, we have the spectroscopic properties of the galaxy. And you can see the correlation of these three principal components by each of these properties. As you can see, for the spectroscopic information, this is only, for the blue part of the spectrum. We can see there is a strong correlation with all of these features. And it could be interesting also because most of these features are considering based on emission line, calculating based on the intensity of the line, while we don't have it here. But when we go through the PC2 and PC3, we cannot find any correlation. Going toward the observable feature of the galaxy and left panel, the most important thing that we can see is that there is a strong correlation between these components and the velocity dispersion, which could be both physical effect and instrument effect, because we know that the velocity, or sigma, is a tracer of gravitational potential of the galaxies, but at the same time, sigma could have a result or effect on the effective resolution of the spectrum. So it could be both instrumental and physical. But at the same time, I was trying to see this correlation to maybe find a trend and answer that, okay, what is the meaning of PC1, PC2, and PC3? But we can see that although we can talk about each subgroup, each component, and see some correlation, but there is not overall trend. And if I go through the red interval also, more or less the result is the same, a strong correlation of PC1 with the spectroscopic picture, not so much for the PC2 and PC3, again, the correlation with the sigma, but we cannot find more answer here, which is in the agreement with the also traditional work that they cannot find these properties of the galaxy as a driven of evolution of the galaxies. So to continue answering the question that what are these components, what we try to do, we try to use the population synthesis model, but as a posterior, to put the physics back to the component that we found. We have the SSPs from EMILES with the fixed IMF of Kurupa, the 3 different metallicity, subsolar, solar, and supersolar, and for 15 different ages. And what I try to do is that I have already eigenvectors by applying the PCA to the SDSS sample. Now, I just want to project this SSP to these components and find out if there is any meaning there. So I project the SSPs to principal component 1, 2, and 3. And what I found is that, interestingly, you can see that the PC1 in both spectral window shows the strong correlation with the age. This circle, star, and cross sign shows the oldest age among the SSP. And we can see for the star-forming galaxy, the blue one, the clump of the galaxy spectra that projected to the PC1 is close to the younger age. When we go to the AGN, it shows more middle age. And when we go to the quiescent galaxy, is more close to the end of the SSP's older age. So there is a strong correlation of PC1, the component that carry most of the information in galaxy spectra, by age. And also we can find this in the red interval. I more focus in the blue part of the spectrum because we know that there are more variance, there are more absorption line. We have the DN 4000 or 4000 angstrom break there, but if you wanted, we can talk at the end of the talk about the red interval as well. And another important feature that we can find here is that I had 3 different metallicity and 15 different age, This is exactly the same plot, was just only its video, but you can see that change in metallicity, which here it shows with different type of line. We have dashed line, dot line, and solid line that shows different metallicity, but change in metallicity is equivalent to change in age, and we can see age metallicity degeneracy here strongly, even while we don't have any emission line and any continuum. This is very, very fundamental, and it's only based on the blind source separation, but still we can find the age metallicity degeneracy strongly encoded in the galaxy spectra, that we can find it in the absorption line as well, as you can see here. To continue our study and understand that, okay, we find out that our first component has a strong correlation with age, but still, what is this component? And what are the difference between these clumps? What I try to do is that I try to consider, for example, consider this red clump, which is the quiescent galaxy projected to the first principal component. I consider the galaxy with a low value of PC1 and high value of PC1. I create a stack spectrum of these galaxies with the lowest value and highest value, and I try to do the SSP fitting. So exactly the same SSPs that I use now here, I compare them with a stack spectrum of the galaxy with the lowest and highest value of each component. This is a simple chi-squared fitting. And you can see that the red clumps here, which shows the galaxy with the lowest value of PC1, and also the blue clump, both again shows a strong correlation with the age. You can see that this red clumps has a younger age, and when we go toward the highest value of the PC1, we have an older age. And another thing that is interesting here is that if we go toward from the quiescent to a star-forming galaxy, you can see that we are going toward the younger age, which is, of course, we already know that, for example, star-forming galaxies are younger than the quiescent. But again, this is interesting for us because it's totally information-based. It's only blind source separation, and we didn't know anything about this, and we find it out. Another thing that is here again interesting is age metallicity degeneracy. You can again find out that when we go toward the quiescent galaxy, the older population, if we go from a star-forming to quiescent galaxy, age metallicity degeneracy increase, which is again based on the fact that we know that for the older population, the amount of entanglement is higher, and we have higher age metallicity degeneracy. Going toward the PC2 and PC3, what is interesting is that it seems that these higher order components are more sensitive about the properties within each sample, not the general trends between different group of the galaxy star-forming AGN and quiescent. For example, here you can find out that for the AGN galaxy, there is a correlation with the metallicity, or here for the star-forming galaxy, we have the correlation between age. And when we go to the red part of the spectrum, this is exactly the same analysis, but for the red part of the spectrum, we find out the same result. So till now, we can see we have one component, a strong correlation with the age, which is everywhere, and it seems that this one component that has a strong correlation with the age and also shows the general trend between different group of the galaxies, the one that carries most of the information. And still we want to continue understanding this component. Before continuing, I just want to here mention the robustness of our results, the fact that I have 3 different covariance metrics and 3 different groups of the galaxy spectra from beginning. Here I just, in this 2 plot, you can see for the blue part and red part of the spectrum, I just have only one covariance matrix. So I have only one covariance matrix. I apply the PCA. I project the galaxy spectra to principal component, and then later on, when I wanted to plot it, I just label them as a quiescent, a star-forming, and AGN red, quiescent, AGN green, and blue star-forming galaxy. And what you found here, you can see that for the first principal components, no matter in the blue part or red part of the spectrum, we can find out that the galaxies are separated in the latent space. and again, AGN is in between the quiescent and the star-forming galaxy. Although, another thing that's happened here, we almost lose any information about a higher order component PC2 and PC3. This is another reason that I was mentioning from the beginning, that if I just only consider one covariance method and whole sample, then because of the mixture of this different population, I am going to lose the information. And that's the reason that from beginning we separate the sample. Another thing that for testing the robustness of our result we did is that choosing the spectral interval. We try to go more radar also in the spectrum. As you can see here, I include the 58 to 62,000 angstrom also. And this shows only the comparison between the first principal component, PC1. As you can see, again, in the blue part, it seems that we have more information and more variance is encoded there. Also, when we go toward the red, the amount of information is less. We can also understand this because we have less absorption line, the amount of the absorption line, the Balmer absorption line in the blue part is more. And also, this is in agreement with the entropy-based study, the entropy-based study that Ignacio did in last year also shows that in the blue part of the spectrum, we have more information. So to continue our analysis, now I want to use the synthetic spectra. Till now, I was just using only SDSS galaxy spectra, but what if I go and use the simulated galaxy spectra that I have the formation history, I have all the past of the galaxy, so maybe then I can understand that what is this one component that sort of control the galaxy formation evolution. Here, I have two simulations, TNG 100 and also Eagle, but I want to compare this simulation with the SDSS result and we consider the SDSS galaxy spectra or observed galaxy spectra, let's say, as a real universe. I know that it's very small, but let's consider it as a real universe. First of all, I need to do the homogenization between these two samples. What I did is that for the SDSS galaxy spectra, I choose the velocity dispersion range to choose the galaxy. But here I cannot do it because we know that the velocity is a parameter that is not trustable or is not accurate in the simulation. So we use a stellar mass, and I try to homogenize each of these simulation sample with the SDSS sample based on the stellar mass. I considered a stellar mass bin, and within each stellar mass bin, I shuffle the galaxies, and I choose randomly the number of the galaxies in a way that the fraction of the galaxy in each stellar mass bin for the SDSS sample and simulated sample is the same. What's happening is that for sure we are going to use so many galaxies, as you can see also here in the primarily plot of stellar mass, the histogram of the stellar mass between the simulation and SDSS. The overlap that we have is very small, so we use so many galaxies. As you can see here for the TNG, from almost 80,000 galaxy, I reach 6,000 galaxy, and for the Eagle, from 78,000 galaxy, almost 3,500 galaxy. It remains after homogenization. So now that I have the homogenized sample of the simulated galaxies, I can continue a study. But sorry, I forgot to mention that from here, I mean, the results before based on the SDSS is published, but now from is only preliminary result, and it's my thought thinking loudly. So it's not anything fixed, I mean, just undergoing. Then another step that I need to do, again, like the SDSS, I need three separated group of the galaxy spectra, which is really, really difficult to do this in the simulation, and we face so many problems. In the SDSS, I had the BPT classification because I have emission line in the spectra, and I can separate the galaxy based on the intensity and the fraction of the emission lines, but I don't have emission line in the simulated galaxies. So what can I do? What we try to do is that, sorry, maybe the name of the axis is not clear. The vertical axis is the Eddington lambda, which is simply the fraction of accretion mass and black hole mass, and shows the growth of the black hole in the galaxy. and the horizontal line is axis is the specific star formation. So I try to separate the galaxy within each simulated sample based on the Eddington lambda and a specific star formation. The top panel shows the Eagle galaxy, the homogeneous sample, and the lower panel shows TNG galaxy. As you can see, first of all, we can see one of the big difference between these two simulations. I have a scatter in the Eagle galaxies in the Eagle spectra, while I cannot find any scatter in the TNG, and it's just everything along a line, which is related to the different subgrid physics of these two simulations. And when I want to choose the galaxy as the AGN, which we suppose that are galaxy with a high specific star formation rate and also high Eddington and lambda, that they have a big black hole, if I choose this for the TNG going towards the right side of the spectrum, I end up by having so many AGN galaxies, which is not comparable with my real universe or SDSS. Because of this, I move a little bit my criteria toward the left, and this green area that you can see is the AGN galaxy, while for the Eagle galaxy, if I choose, will end because I don't have so many galaxies actually here, is okay. Another thing is that maybe someone says that, okay, you bias the result. I agree. In this way, I bias the result. Maybe a little bit, but this is the only way that I can have the same fraction of the galaxy in the Eagle, TNG, and SDSS galaxy. And another thing is that maybe I can also say that I don't consider the composite galaxy or galaxy with a low star formation or low AGN activity. So then maybe we can consider this galaxy with higher star formation rate and also high Eddington of lambda as a composite galaxy. So maybe even it's better that we remove them, because in the BPT classification of the SDSS galaxy, I just choose BPT equal to -1 for the quiescent, which means really dead galaxy, and BPT equal to 1 for the star-forming galaxy, which means really high star-forming galaxy, and BPT equal to 4 for the AGN galaxy, which means almost safe-red AGN, or galaxies that have a strong AGN activity. In the SDSS sample also, I don't consider composite or low star-forming and low AGN. Okay, having these three group, maybe even not very well separated, let's continue. And here also, I just wanted to show the fraction of the galaxy that I have within each subsample, SDSS, Eagle, and TNG. I try to have the same fraction in the Eagle and TNG as SDSS, because I consider SDSS again as a real universe and I want to be comparable with it. Another thing that I wanted to show in this two plots, which is the stellar mass based on the specific star formation, and what's interesting for me is that AGN galaxy in the TNG it will be at the top of the star-forming galaxy. There's a strong overlap, while in the Eagle is not in that way. You can say that, okay, it's because of the way that I select them. I agree, but let's continue a study and you will find out the difference. Now that I have the simulated galaxy separated, like when I project the SSP to this component that I already find out through the SDSS analysis, I do the same. I have PC1, PC2, and PC3 based on the PCA analysis over the SDSS galaxy spectra. And now I just project these three group of galaxy spectra of the simulated of Eagle and TNG to the component that I already have. And you can see that, interestingly, even through the simulation that we know that it's not very well and perfect, we can find out that the first principal components separate different galaxies. But what is interesting for me here is that you can find out there is an overlap between the AGN and star-forming galaxy, no matter in Eagle or TNG. In the TNG, I expected it because the way that I choose the TNG galaxy, you can see the way that I choose the TNG galaxy AGN, were at the very, very overlap with the star-forming galaxy, while in the Eagle wasn't in that way. But still, you can see that the amount of overlap is almost the same. Another thing is that we can see both simulations put the quiescent galaxy away. That when I look on the median spectrum of these two groups, this is TNG, this is Eagle, you can see that the median spectrum shows that the difference between the quiescent star-forming and aging galaxy is bigger than the Eagle. And interestingly, this is here in the latent space. You can see for the Eagle, there is a bit of overlap between the quiescent and other two. But here we can see that it is totally separated because the difference between their median or their feature is bigger. This is another proof that the way that we separate the galaxy spectra in 3 subsample, it's not a disjoint comparison, because if that was a disjoint comparison, I cannot see it here in the latent space. So, okay, now I have this latent space. Again, continuing, what are these components? Exactly the same as SDSS. I consider the galaxy with a low value and high value of PC1. I create a stack spectrum and I do the SSP-PT. But this here, I just only show PC1. You can see, I mean, we already talked about the SDSS one and the correlation with the age, but when I go to the Eagle and TNG, you can see still, again, it's not the correlation with age. There is a correlation with both age and metallicity. Here, this is an important result because it seems that the Eagle and TNG galaxy spectra, it cannot represent our real universe very well. While we see that only age correlation, here we can see that there is a correlation with metallicity as well. I try to look at the spectrum, at the star formation history of this galaxy. What is different in the star formation history of this galaxy that I can see the age and metallicity, both correlation with the first principal component? When I look at the star formation history, this is the CDF of star formation history for the galaxy with a low and high value of the PCR in 2 simulations, Eagle and TAG. What is interesting here, you can see for the quiescent galaxy, that was the galaxy put away and in very, very far away, not very, very far away, but different than the AGN and star-forming galaxy in the latent space. The speed of formation is different between the galaxy with low value and high value. We can see that there is a group of galaxy with a high value as visible that we had a quick formation, very quickly a star forms and done. But then we have the slower formation for the galaxy with the low PC1. So it seems that in the simulation, we can maybe say that the star formation, the underlying subgrid physics that controls star formation, then controls the feature of the galaxy spectra, and we can find that there is an age and metallicity correlation both with the variance of the galaxy spectra. Here is the results that I found through the comparison with the simulation, but still I need to take into account with a more careful and with detail the difference between the subgrid physics at TNG and Eagle and find out that why still I have this metallicity correlation. Maybe it's as simple as that the Eagle and TNG galaxy spectra cannot represent the real universe. But maybe there is another meaning also here, because you can see that for the AGN and the star-forming galaxy, more or less, the formation history is the same. And the average age is the same. But when we go toward the quiescent galaxy, the average age between the galaxy with the low PC1 and high PC1 is different. So maybe, again, based on the analysis of the galaxy spectra, based on the variance and multivariate analysis, we cannot go further than average age and metallicity, and we are very limited, and we cannot extract more information from the galaxy spectra. So this is now my results, and thanks for paying attention. If there is any question or comments, I will be happy to talk. Hey, are you there?
Thanks a lot, Zahra.
Welcome.
Tefka is muted, but people are clapping. Well, thank you very much, especially for giving us the talk under these conditions and the difficulties with the voice. Any question in the room?
Hello.
Hello.
This is Elena Dominguez speaking. Thanks a lot for the talk. It was very interesting. I have a lot of questions, but I'm going to do a fast one. Did you test what is the effect of the meaning of the PCAs when you compare with the signal to noise of the spectra?
Yes. Actually, at the beginning, I wasn't restrict the signal to noise ratio to be, very high. And when we have more noisy spectra, I would say that the signal will be lost. I can't pick up anything. So it's very important to consider the signal to noise ratio and noise also. And sorry, I forgot to mention this, that for the Eagle and the TNG synthetic spectra, I also add the noise. Which is equivalent to the SDSS galaxy spectra, because it's very important. Yeah.
Okay, but do you see any correlation? Like you see a correlation with the mass? So I was wondering if that correlation may be due to the signal to noise. Also because the variance that you get from your PCA is very small, right? You capture only, 13% of the variance with the 3 components? So I was wondering, where do you think the rest of the variance is included?
I think I mentioned this, and also I tested this. The rest of the variance is in continuum. If I include the continuum, I am going to capture almost 90% of the variance in the galaxy spectra only using 3 components. The rest of the variance is in the continuum, but the reason that we remove the continuum is we know that there are lots of dust reddening in the continuum. And also we know that the flux calibration cannot be, maybe it's not very perfect, and then it will be picked up by the PCA. There are so many studies that talks about the flux calibration and correlation with the PCA. So because the input information is variance, it's important that we remove everything, and we wanted to focus on the stellar population. So we thought that it's better to remove the continuum and just only having the stellar population, see that if there is something encoded there.
Okay, thanks a lot. Very nice talk.
More questions in the room? Alessandro?
Yeah, like Elena said, very nice talk. Actually, I have a very basic curiosity. Because you said that in the Sloan spectra, you remove the continuum. And every time someone removes something, I get scared. So can you expand on how you remove the continuum?
Yes, it's not fitting, because most of the time people remove the continuum by the fitting. It's called BMC method, or boosted mean continuum, or pseudo continuum. What I do is that I consider the 90th percentile of the spectrum, and I prove the shape of the spectrum, and I remove it from each spectrum. I think there is a paper from Ben Rogers in 2010 or 9 that they described this method. So it's not the model. I don't fit anything. It's just that I prove the shape by consider the 90th percentile of each spectrum, and then I remove it. They called it boosted mean continuum, or pseudo continuum.
Thanks.
Welcome.
I have a question. What would be the effect of the contribution of the accretion disk from AGNs on the eigenvectors? So can you have like dilutions of the absorption features that you're looking for that might affect the interpretation of the
To be honest, I didn't look at it yet, because the result of the simulation is very recent. But yeah, that could affect it, especially I think because the way that I consider, I choose the AGN galaxy, it's mostly based on the Eddington lambda, and Eddington lambda also is the accretion mass, accretion rate divided by the black hole mass rate. So I think, yeah, for sure it could affect it. And also the way that maybe we define AGN activity or we implement AGN activity in both Eagle and TNG, because we know that in the TNG at a specific stellar mass, we suddenly turn on AGN and then we end up having so many AGN. So yeah, that could be a correlation there, but I didn't look at it in detail yet.
Okay. More questions? If anybody's raising his hand and I don't see it, he or she can directly speak. Okay, if we don't have many more questions, we thank again Zahra for this very nice talk.
Welcome. Thank you all of you so much for listening to me. Thanks a lot, and I'm again sorry about my voice and the cold.
Take care.
Thank you for the effort. So thank you very much, guys.
Thank
You are dismissed.
Bye.
Bye.